last time we stopped here talking about hybridizations, different hybridizations in SP, SP2, SP3, and I covered this subject, and I showed you how to get the hybridization for any element, like say carbon, and also we showed how do we form the two pi bonds. Okay, so we're going to continue the discussion talking about the hybridization, and we'll start with this question. Okay, the question is going to be, okay, which bond is stronger, a pi bond or a sigma bond? Okay, what's the difference between pi and sigma bond? Okay, remember that in order to get a sigma bond, we need to have head-to-head interaction. Okay, head-to-head interaction. So the green one with the yellow one, if they're reaching each other, now there is a minimum distance between them because it's a head-to-head interaction. Force will be higher, attraction force from each side will be higher. This is going to be a strong bond. Okay. Now, when it comes to a pi bond, we get it through space. Okay, they reach each other through space. They are not close to each other because there is a distance between them. We say pi bond is always going to be weaker. And remember that you're talking about electrostatic forces, and this is the formula that you need to use in your calculation or to understand it. Force is going to be equal to K multiply Q1, Q2 divided by square of the distance between them. Okay, and Q1 you can say the first electron. Okay, and what's a Q2? You can say the proton on one nucleus. Okay, and R is going to be a distance between technically. Okay, distance between electron, okay, from one element and nucleus, okay, where we have positive charges there. Distance between technically between the electron and the electron and the source of positive charge or the attraction force on the neighbor atom or neighbor molecules. And why did I not continue it to the exactly to the center? You can say this is the distance technically between them. That's fine, and call it R whatever. And as R goes up, because R is showing inside the denominator, and Q1, Q2, and K are not changing, only R is changing, and R is inside the denominator. As R goes up, force will go down. What does it mean? It means you will have a weaker bond. A weaker bond. So this is the distance between two p orbitals, and that they are going to form a pi bond for you, versus two p orbital that are attracting head-to-head. And because the distance here is less, force is going to be stronger. So always sigma. Okay, sigma bond, sigma, forgive me, sigma bond, okay, and I'm saying one sigma bond is stronger than one pi bond. Okay, so if we compare sigma to pi bond, sigma is always stronger. Okay, and when you attach two elements to each other, the first bond always going to be a sigma. Okay, so the first bond is going to be sigma. Now, if you build two bonds, the second bond is going to be a pi bond. And if you repeat this one, and you're going to get, again, another pi bond. So this one also is going to be pi bond. And if I continue this one and build four of them, so I will get two pi bonds. And the last one, okay, is going to be delta. Okay, so the fourth one, it will be delta. Second and third one, we call them pi. The first one, always sigma. Okay, as the order goes up, bond will be shorter. Okay, bond will be shorter. So let's call this one 1, 2, 3, 4. Okay, which bond is stronger? Okay, I'm going to say the one that has a quarter is going to be stronger than triple, and that one stronger than double, and the double is going to be stronger than a single bond. That's going to be stronger than single bond. So that means the single bond, it will be the weakest. Okay, this is going to be the weakest bond, and also will be the longest bond. Okay. Okay, so we're going to switch to second question. So sigma bond always stronger than a pi bond. Okay. Now, when it comes to hybridization, we can have sp3 hybridization versus sp hybridization. Which bond is going to be stronger? Okay, the one that has less from p orbital, it has less character, it will be stronger. Okay, the one that has less p character, it will be stronger or technically shorter bond. Okay, what's the reason behind it? Okay, the s orbital is closer to the nucleus. Okay, s orbital is closer to the nucleus, and so we say the more s we have, in sp we have 50% s character, and 50% p character. This one is going to apply higher attraction force on the neighbor, or you can say electronegativity of an SP hybridization. It will be higher than electronegativity of sp2. Why sp2? Okay, because this is going to be 33% s and 67% p character, and the electronegativity will be higher than sp3, which is going to be 25% s and 75% p. Okay, p character. So as p character goes up, we say the bond gets longer, or which is, you can say or equal to, turns to be weaker bond. So as the bond gets longer, it will be weaker. Forgive me, not weaker bond. What did I write for? Yeah. Okay, yeah. Weaker bond. So, okay. So we're going to say SP, it has higher S character, so it will be a shorter bond because it's a stronger bond. Okay. And P, it has 75% P character, so it will be the longest between SP, SP2, and SP3. Okay. Now let's check in the bond length here. The bond length, I'm talking about this specific bond. Okay. And the bond is getting shorter and shorter. Why? Because for that carbon, the hybridization is sp3. How about this carbon is sp3? Here, sp2, that one also sp2, that one is sp, and here is sp. I already showed you how to get the hybridization for them. Okay. As you increase the S character, the bond gets shorter. So from 1.54 angstrom, we went to 1.2. The bond got shorter. When the bond is shorter, in order to break it, you need to spend more energy to break it. So what's the bond energy here? It says bond energy. This is the energy that you need to spend to break it, right? To break the bond. And sometimes we call it bond dissociation energy. Bond dissociation energy. You need to spend 120 kilojoule to break a triple bond. Because it's a shorter, it will be harder to break it. Okay, again, the science behind it is hybridization. Okay, now it says which one of this has the longest CH bond. Okay, and if I give you such a question, just simply try to figure the hybridization of carbon and see like which element the hydrogen is attached to it, and based on hybridization, try to judge, judge them and find the correct answer for it. Okay, so if I want to go after this question, I'm going to say, okay, this carbon, the one I'm highlighting, this carbon is surrounded by 4 sigma bonds. Okay, 4 sigma bonds. So I have 4 sigma bonds. What's going to be the hybridization? I'm going to use 1 from S, and I will add 3 from P to it. I get 4 orbital of S1, P3. So the hybridization is going to be sp3. Okay, hybridization will be sp3. How about here? Okay, this carbon is surrounded by 1, 2, 3 sigma, and the last one it will be pi bond. We don't care about the pi bond, so I'm going to say I have 3 sigma. I need to use 1 from S and 2 from P. That's going to give me 3 orbitals of S1 and P2. So the hybridization is sp2. And last one, we go sigma here. We have a sigma there, and this is another sigma. And then we have 2 pi bonds. Okay, we don't care again about the pi bonds. So I have 2 sigma bonds. I'm going to say I need 1 from S and 1 from P. That's going to give me 2 orbitals of S1, P1. Okay, so the hybridization for those carbons, I got sp3 here. There I got sp2, and this carbon sp. Okay, remember we said as we increase the S character, the bond gets shorter. Okay, the bond gets shorter. It means it's getting stronger. Okay, so what's the strongest bond here? The strongest bond is the one that has the sp hybridization, and then CH with sp2. The last one will be CH with sp3 hybridization. So the weakest one, it will be sp3 hybridization. Okay, so let me just erase this one. Okay, I'm going to move it. Put this one here. Okay. Strongest bond, it will be the number, it will be the part, C. Okay, C is going to be the correct answer. and it will be the strongest bond or the shortest bond, technically. The shortest bond, it will be C. Okay. So as S character goes up, bonds get stronger and it will be shorter. SP, SP2, and that one is SP3. Okay, cool. So now let's move to valence shell electron pair repulsion theory. And what's this theory? This theory says that whenever you want to build geometry of a molecule, try to put them in a way that you have the maximum bond angle and increase the bond angle. Why? Okay, because you'll have less repulsion. Imagine that I want to connect this to you. Okay, I can put it in this position, it will be 90 degree. Okay, or I can increase it and the bond angle, it will be something around maybe 120. That's good. Okay, because 90 I have more repulsion, 120 it will have less repulsion, and when I increase it to 180 repulsion, it will be minimum. Okay, so try to put the two bond pairs. This is one pair and that's a second pair. Put them way far from each other until you get the maximum bond angle, and your system will be stable. Okay. How do I get the geometry? Okay, how do I get, for example, the hybridization, and what's the role of the lone pair? Okay, let's practice this one. Okay, so instead of following the slide letter by letter, let's start with this. Imagine you have such a molecule. You have AB2. Okay, AB2. And what's the AB2? AB2, I have one central atom attached to two outer atoms. I go with BeCl2. Okay. Beryllium is a group 2. So it's not going to make it to octet. Chlorine is a group 7. So I'm going to say 1 beryllium plus 2 chlorine. 1 multiply 2 electrons plus 2 multiply 7, I get 16 electrons. Next, electronegativity of chlorine higher than electronegativity of beryllium. What does it mean? It means Be is the central atom. Okay, put the chlorines around it. Okay, so we're going to put the chlorine here. We will use 2 electrons there and 2 electrons here to make 2 sigma bonds. Okay, so out of 16, I use 4 electrons to make 2 sigma bonds. I'm plus 12. What do I do with the 12? Okay, you will draw a circle around each element. Okay, and you start with outer atoms, chlorines. You give each chlorine 6 electrons until you make it octet. Okay, minus 6 multiplied 2 times. So I use all the electrons. Now I'm 0. Okay, how about the central atom? Central atom clearly is not octet. You can test it, but central atom will not make it to octet because it has only 2 electrons. It will share it with 2 neighbors. Max, it will get 4 electrons. Okay, now I go here, 7 electrons plus 1 sigma bond, 8, 7 plus 1, 8. I got 2 sigma bonds. How about the central atom? 2 plus 2, 4. Okay, it's not octet. That's fine. The central atom, because the group 2, will not make it to octet. Group 2 and group 3, 2 and 3 will not make it to octet unless you pair electrons from neighbor. But if you do it, a formal charge, it will be either positive, a big positive number. Yeah, there's high chance it will be a positive number, and that's going to make the system unstable. Let's check the formal charge. Okay, so formal charge. Chlorine is a group 7. How many electrons do I see? I see 7 electrons around it, so 0. Okay, again, 7 minus 7, it will be 0. How about beryllium? It's a group 2. How many electrons do I see around it? I see 2 electrons around it, 0. So I got all the formal charges equal to 0. This is perfect Lewis structure. Okay, this is perfect. Yes, the central atom is not octet, and I get it. Okay, now let's go after hybridization. We have 2 sigma bond for Be. Okay, how about lone pair? Okay, sigma plus lone pair. Do I have lone pair on Be? No, I don't have. Only the central atom. And what's a lone pair? Those 2 electrons, we call them lone pair. And blue one, we call them bond pair. So I don't have any lone pair on beryllium. So I say 0. Okay. 2 plus 0, that's going to be 2. Okay, so what's going to be the geometry? Expected geometry, okay, expected geometry, when you have two pairs, it will be linear. Okay, and I have two pairs. That means I have 4 electrons. Okay, that means I need 2 hybrid orbitals to accommodate those 4 electrons. Okay, let's start with 2. Okay, here we go, 2. We're going to use 1 from S. We need 1 more orbital. Remember, always you have 1 from S, 3 from P, and 5 from D. Okay, so we're going to use 1 box from S. Then we need 1 from P, and that's going to give us 2 orbitals of S1, P1. Okay, so the hybridization, it will be SP. Okay, next. This is beryllium. It has 2 orbitals, 2 hybrid orbitals. Okay. And beryllium is a group 2. Group 2, so you have 1 electron up here, and those are sp orbital. Sp orbital. Now show the chlorine. Chlorine is going to reach from this direction or that direction, and that's going to be chlorine. Chlorine will come with 1 electron that is pointing down. Now this interaction is going to be a sigma bond. I got sigma bond. Okay, and what's a bond angle? The bond angle, this is the bond angle that I'm talking about. It bond angle, it will be equal to 180 degrees. So when hybridization is sp, expected bond angle to be 120, and geometry expected to be linear. Okay. So next lecture, I'm going to go through sp2 and sp3 while we have a lone pair. And thank you very much.